The presentation I'm sharing with you today is part of a collaborative study on population dynamics of large river fishes. Fish recruitment and growth are affected by numerous drivers, including the biological environment, resources, the physical environment, and stress. A nearly unreadable multitude of different factors contribute to each of these drivers, including social interactions, food availability and quality, habitat, and various natural disturbances and anthropogenic stressors. Each of these drivers varies spatially within large rivers, thereby creating patterns in fish recruitment and growth. Large rivers are complex and heterogeneous systems with seasonal and spatial variations in their ecology, geomorphology, and hydrology. And of course, these seasonal and spatial variations in environmental factors can affect fish recruitment and growth. However, most studies of fish recruitment and growth in large rivers are focused at relatively small spatial scales, often a single river or even a single reach. Moreover, the limited studies that are available often focus on sportfish rather than non-game or quote unquote rough fish, which can often be integral to riverine biotic communities. For example, gar species are a specific host for yellow sandshell mussel glochidia, and most mussel species can't reproduce without the correct fish host present. So today we're here to address all of those issues with small spatial scales and sportfish biased studies by sharing with you all a study on recruitment and growth of a widely known non-game fish from 4 different Midwestern large rivers. First, we'll meet the star of our story today. Then we'll examine patterns in growth among our 4 rivers. The study also included recruitment, but for the sake of time, I'll just be sharing the growth analysis today. And then we'll explore environmental drivers that may be affecting growth. And finally, we'll explore some management implications that come out of our study. But first things first, let's meet the star of today's show, the drum. Oh, that's not right. That's the wrong drum. I'm sorry. This is the right drum, the freshwater drum, also known as sheep's head, purple perch, gray bass, croaker, grunter, and one name that doesn't make any sense unless you speak French Cajun, gaspergou, which means to break shellfish. The freshwater drum, which today I'm just going to call drum, is a long-lived benthic generalist that is recreationally and commercially important in large Midwestern United States rivers. Drum are also ecologically important as specific hosts for several freshwater mussels, many of which are endangered. We harness the power of a highly standardized regional sampling program to examine numerous environmental factors we believed would regulate drum recruitment and growth at broad spatial scales in large rivers. The long-term survey and assessment of large river fishes in Illinois, historically LTEF for short, began in 1957 as an AC electrofishing survey on just the Illinois and Des Plaines rivers, but expanded in 2010 to include pulse DC surveys on the Illinois portions of the Illinois, Mississippi, Wabash, and Ohio rivers. We and our statewide partners collected drum during our standardized surveys on these 4 large rivers during 2017 and 2018. Given the spatial breakdown of navigational pools and open reaches that we sample, and also the patchy availability of environmental covariate data, we divided our rivers into 8 broad regions. And thanks to our partners in the UMRR LTRM program, we were able to add Pool 8 on the Mississippi River as well, giving us 9 total regions. We collected at least 54 fish from each region except the Upper Illinois River, where we were only able to collect 24, but still had nearly 1,000 fish total for this study. We removed, dried, mounted, and sectioned drum sagittal otoliths, and then assigned age estimates to digital images of each section. One of my favorite things to do in a presentation like this is to put up a picture of an otolith and then take it away before the audience can count all of the annuli. Us fish squeezers just can't stand that. We measured incremental growth between the annuli and used mixed effect linear models to determine year-specific growth estimates, and then investigated environmental influences on yearly drum growth. This graph shows the 9 sampling regions along the x-axis, maximum total length along the primary y-axis and with the orange bars, and maximum age along the secondary y-axis and with the white dots. Max total length ranged from 450 millimeters in the upper Mississippi River region this fish here, to just over 700 millimeters in the lower Illinois River region, right here. Max age ranged from just 12 in the upper Mississippi River region, right here, to 34 in the Pool 8 region, up here. Now I'm going to share paneled graphs of year-specific growth, corrected for individual fish, age, and birth year. Year is along the x-axis in the middle of each graph, and points above the x-axis indicate years with better than predicted growth, whereas points below the x-axis indicate years with worse than predicted growth. The black dots and lines indicate the mean predicted growth, whereas gray shading indicates standard error. Across the 8 regions, there is a lot of variability in growth within and among years, but there doesn't appear to be any broad-scale synchrony. Yes, I know I don't have these graphs labeled by region, but that's done intentionally, as I want you to focus on the patterns, not the locations. Of the 8 regions we were able to model, we had too few fish in the upper Illinois to be able to model it successfully. There was only 1 year that was quote unquote really good in at least 3 regions, and that was 2005, indicated by the orange arrows. Similarly, there was only 1 year that was really bad in at least 3 regions, and that was 2014. 2 of our regions shared the good and bad years, the upper and lower Wabash River. Now this is logical because, as everyone who's ever heard a presentation from a fisheries grad student at Eastern Illinois knows, the Wabash River is the longest free-flowing river east of the Mississippi. All jokes aside, perhaps locks and dams present in our other regions are affecting drum populations, but that's something we'll save for another day. Overall, however, we did not see much for consistency or synchrony in year-specific growth at that larger basin-wide scale, which suggests local effects may be more important. So let's explore those local environmental drivers now. We know that fish recruitment and growth in lotic systems is driven by environmental factors like water temperature, river discharge, and food availability. So we queried long-term climate and hydrology stations to acquire air temperature data as a proxy for water temperature, river discharge data, and we used various long-term fisheries data sets to index interest-specific competition for prey resources for young-of-year drum. We partitioned our temperature data into 4 independent variables: maximum summer temperature and growing degree days, which is the total number of days in a year with the mean daily temperature above a threshold, often 10 degrees C, and then minimum winter temperature and heating degree days, which is the total number of days in a year below a temperature threshold. Growing degree days and heating degree days are a useful integrative measure of how warm or how cold a year is, whereas maximum summer temp and minimum winter temp are a more useful measure or a specific measure of how extreme cold or warm a year is. We also partitioned our discharge data into mean daily discharge for the growing season, which we defined as March through November, and for the winter season, which we defined as December through February. We compiled silver carp catch per unit effort data, or CPUE data, from our program's surveys, but also included CPUE data from Illinois DNR and LTRM surveys. We think silver carp will likely have more of an effect on drum recruitment, but since we included them for growth too, we had the data. This table shows the environmental drivers across the top and the 8 sampling regions along the side. The first row there is for all of our regions pooled together. This is just the first cut through these environmental drivers, so we started with simple correlation and are saving higher level modeling analyses for a different day. The only variable that was associated with drum growth for all regions pooled was max summer temp, which has a positive association. This makes sense from a bioenergetics perspective, as warmer temperatures, up to a point of course, increase fish growth. When we examine region-specific associations, max summer temp was positively associated with drum growth in 4 of our 8 regions: Pool 8, the open river region downstream of St. Louis, and both the upper and lower Wabash. Growing degree days was positively associated with drum growth in 2 regions, the lower Wabash and Ohio rivers. I'll point out that maximum summer temp and growing degree days are not significantly correlated with each other. Heating degree days was negatively associated with drum growth in 2 regions, the lower Illinois River, and Pool 8 on the Mississippi River. This also makes sense from a bioenergetics perspective. A longer period of colder temperatures likely inhibits growth. Growing season discharge was negatively associated with drum growth in 3 of our 8 regions: the lower Illinois River, upper Wabash River, and Ohio River. Again, this makes sense as higher discharge could increase basal metabolic rate or influence fish to move to off-channel habitats with lower quality foraging opportunities. Winter discharge was positively associated with drum growth in 2 regions, the upper and lower Wabash. This one made us scratch our heads a bit, but we speculate that it may have to do with either moderating cold winter temperatures or providing access to different habitat than is available at lower discharge. We're not quite sure and want to investigate this further. Here's a couple of examples of what the association between growth and our environmental variables looks like graphically. This first example is heating degree days in the lower Illinois River, which has a negative association with drum growth. So when heating degree days, shown by the purple line, are high, growth is low, and vice versa. On the other hand, maximum summer temp was positively associated with drum growth in Pool 8 of the Mississippi River, and you can see the bright green line tracks the black dotted line really well, almost perfectly from the late 1990s onward. As I mentioned, this is just the first cut through these environmental data, but we're currently working on some higher level modeling analyses that will hopefully explain some of these associations more fully. All right, let's recap a few highlights from our river journey today before we drill down into what it all means. First and foremost, and I can't say this enough times and enough places, non-game fish are ecologically important. They are integral members of the biotic community and play critical roles in large river ecosystems. Second, our study shows that freshwater drum growth does not appear to be driven by broad-scale environmental factors. Rather, it is driven by regional factors that vary across rivers. Third, freshwater drum growth was driven by temperature and discharge, which certainly makes sense from a bioenergetics perspective. So what does this all mean? What can fisheries and river managers learn from this study? First, that regional partnerships like we have in Illinois are incredibly valuable. Being able and willing to share data across rivers, working on a statewide or even larger scale, can help reveal and explain patterns that we might not see at smaller scales, especially for large river fishes that might not be constrained to a single navigational pool throughout their life history. Second, I hinted at the possibility that locks and dams might isolate drum populations, as the upper and lower Wabash River regions shared a lot of similarity in several aspects of our study. I acknowledge that it's just one example, but we think it warrants further investigation and certainly has broader application beyond just this one species in one state. Third, and perhaps most importantly, given that drum growth in our study regions was driven by temperature and discharge, climate change could affect not only drum populations, but also other fishes and the larger biotic community as a whole. Changes to the seasonality and amount of precipitation and changing thermal regimes, both of which are predicted by Midwest climate change models, could have serious consequences for our large river ecosystems, almost all of which have been anthropogenically simplified, causing a myriad of negative consequences. My take-home message today is that non-game fish play a critical role in heavily modified larger ecosystems, and that broad-scale collaboration can help us better understand and manage these amazing critters and the critical resources they represent. I thank you for watching our presentation and look forward to hearing any questions you might have.